Nobody was paying attention to 3 Atlas until the leaked images surfaced. Suddenly, what had been considered a benign interstellar comet no longer seemed harmless. Within hours, the UN quietly activated a global defense protocol, typically reserved for incidents that never reach the public eye. The American people have both the right and the responsibility to know the truth about unidentified aerial phenomena. That truth, however, remains concealed, classified, and suppressed by fear, retaliation, stigma, and uncertainty. Telescopes were redirected, agencies fell silent, and the tracking priority surged to the highest level. So, what exactly appeared in those leaked photos? Why did the UN respond in this manner? And what is 3 Atlas doing that no one anticipated? A new scientific priority had emerged. When 3Y Atlas was first recorded in July 2025, it entered databases like any ordinary new comet: position, brightness, preliminary estimates, and provisional designation. Nothing about those initial entries suggested it would become a focal point for the world's planetary defense network. Yet, over the following months, astronomers noticed anomalies uncommon in newly discovered objects. Data from multiple observatories failed to align neatly. Most solar system comets behave predictably once sufficient observations are collected. Their orbits stabilize, and their activity follows established patterns. 3IA Atlas did not. Minor inconsistencies appeared in calculations, and the comet's dust geometry varied between image sets. These variations were subtle but persistent. Persistence attracts the attention of organizations monitoring the sky. By mid-October, the Minor Planet Center had compiled enough reports to warrant a coordinated approach. Instead of relying on scattered telescope submissions, they prepared a formal announcement to synchronize the world's observatories. An internal bulletin was distributed in late October 2025, requesting national space agencies and independent facilities to provide coordinated data on 3 Atlas through the end of January. There was no suggestion of a crisis. It wasn't necessary. In astronomy, consistency is crucial, and 3 Atlas offered none. Its interstellar origin made the discrepancies more compelling. Material formed around a different star behaves differently near the Sun. Scientists needed a clearer picture of these behaviors in real time. A structured, multi-month campaign was the most reliable method to capture that activity. Once the notice circulated, observatories from South America, Europe, and East Asia added 3 Atlas to their tracking lists. Some monitored brightness changes, others focused on its position relative to background stars, while a few studied the unusual dust patterns already noted by amateur astronomers. Together, their data created a continuous record of the comet's motion. In the weeks following 3Y Atlas's inclusion in the global campaign, researchers revisited the fundamentals. Interstellar objects are rare, and each new discovery forces astronomers to reassess assumptions. 3 Atlas fit that pattern immediately. Unlike comets formed alongside the Sun, this object came from another star system and carries a chemical and structural history shaped by conditions not fully understood, making it valuable. Its motion added to its uniqueness. The first clue was its hyperbolic trajectory. Most comets follow elongated ellipses, returning to the Sun over hundreds or thousands of years. 3 Atlas follows a path that doesn't close. It entered interstellar space and will leave the solar system, giving astronomers only one chance for close observation. Its speed, exceeding 200,000 kilometers per hour, reflects this origin. Objects moving this fast are less influenced by solar gravity, so their paths respond differently to outgassing and solar radiation. Comet activity complicates trajectory models. Sunlight warming a comet's surface produces gas jets that slightly alter its course. Normally, these effects are small but predictable. With 3 Atlas, the pattern was unclear. Some observations suggested extra momentum inconsistent with the nucleus's expected shape. Others showed brightness fluctuations that didn't match the usual day-by-day cycle of typical comets. These weren't dramatic anomalies, but indicated that more data was needed to understand how this object reacted to the sun. Amateur observers contributed images revealing a distinctive dust configuration, including an anti-tail, a thin particle line pointing toward the sun rather than away. Rare, but possible when dust spreads along the orbital plane and is illuminated from the right angle. This feature encouraged detailed study of dust interactions with solar radiation and internal comet activity. As more telescopes tracked 3-2 Atlas, one feature stood out. The dust didn't behave as expected for a classic comet tail. In early November, images from Spain, Japan, Canada, and Chile circulated within research groups, all showing the same structure, a long, thin streak roughly pointing toward the sun. To the untrained eye, it appeared reversed. To astronomers, it signaled a geometry worth studying. The anti-tail, formed when dust spreads along the orbital plane and is illuminated at a particular angle, was clear and persistent. Over consecutive nights, small telescopes captured sharp images, suggesting an unusually structured dust distribution for an interstellar visitor. At the same time, the comet's brightness varied irregularly, not matching its distance from the sun. Early photometric readings didn't align with expected activity for its size. These deviations, while not extreme, raise questions about how material from another star system responds to solar heating. The coma, the gas and dust cloud around the nucleus, added further intrigue. Amateur images showed it elongated rather than spherical, implying surface activity concentrated in certain regions. While asymmetry isn't rare, in an interstellar comet it becomes a crucial clue, hinting at compositional differences, structural variations, or temperature-driven effects not seen in long-period solar system comets. Once multiple observatories submitted consistent measurements, researchers anticipated the orbit would stabilize. For most comets, this process is straightforward. Each observation refines predictions and reduces uncertainty. 3 Atlas, however, resisted stabilization. Minor offsets appeared between predicted and measured positions, drawing attention. Interstellar material often contains volatiles that behave unpredictably under new temperatures and sunlight. Gas venting produces subtle, non-gravitational effects. What distinguished 3-2 Atlas was the frequency and timing of these shifts. Deviations occurred even at distances with modest comet activity or without correlated brightness changes. Its motion wasn't erratic, but modeling required detailed, continuous data, justifying the 2-month global campaign. Dust orientation complicated modeling. The anti-tail combined with an asymmetric coma made estimating nucleus size and shape difficult. A spherical nucleus interacts differently with sunlight than an elongated, unevenly active one. Early images suggested 3 Atlas was not a simple sphere, adding complexity to orbital calculations. Accumulating data revealed that this object offered a real-world test for planetary defense systems, not because it was dangerous, but because it was fast, interstellar, faint at times, and inconsistent, challenging standard tracking tools. Agencies could test data flow, modeling accuracy, and prediction reliability under genuine conditions. Its interstellar origin further increased its value. Such objects deviate from established patterns, with variable compositions and activity levels, making detailed study crucial as survey telescopes detect more interstellar visitors. The campaign also allowed agencies to practice multi-institution collaboration. Hemispheres shared data, software teams updated orbit solutions, and photometry labs compared brightness curves. This wasn't a crisis, but a demonstration of global readiness under safe conditions. While space agencies managed operations, academics pursued scientific insights. Harvard stood out due to ongoing interstellar research since Oumuamua in 2017. That object left questions about shape, structure, and acceleration. By 3 Atlas's arrival, frameworks for studying interstellar objects were well developed. Harvard scientists viewed it as a key data point. Composition was a major focus. Interstellar comets may contain unusual ices that sublimate differently, reflect sunlight oddly, and influence dust distribution. The anti-tail and asymmetric coma hinted at a non-uniform surface or volatile mixture reacting irregularly to solar heating. Brightness variations offered indirect clues about rotation, surface texture, and activity. Harvard treated it as a physics problem. How does a comet from another star respond to solar radiation? Which materials sublimate first? Which jets drive non-gravitational forces? Imaging presented surprises. High-resolution instruments, including Mars-orbiting spacecraft, produced softer, less detailed images than anticipated. The comet appeared faint and diffuse, lacking visible structure. Amateur astronomers, using 20 to 30 centimeters telescopes, produced images highlighting features barely visible in NASA's releases. The anti-tail and hints of an elongated coma appeared clearly, illustrating the comet's directional activity. This discrepancy reflected imaging challenges. Spacecraft cameras optimized for planets struggle with faint, fast-moving comets. Ground-based amateurs adapted exposure times nightly and processed sequences for faint targets. This dynamic created a division of labor. Professional facilities provided precise positions, while smaller telescopes revealed dust details. Observers treated this as complementary strengths rather than contradiction. The UN's involvement became public with a notice confirming the 2-month campaign. Starting November 27, 2025, participating observatories followed a unified schedule monitoring position, brightness, and dust behavior until January 27, 2026. Rarely commenting on individual comets, the UN's announcement reflected planetary defense coordination under its asteroid warning network. The statement emphasized that 3 Atlas posed no threat, but underscored its scientific value. Interstellar objects pass quickly. Data collected provides a long-term reference for future study. Coordinated observations reduced measurement scatter from equipment differences, weather, and timing, producing a cleaner record of the comet's path. Each facility contributed distinct observations, creating a composite dataset stronger than any single source. The campaign also tested how rapidly information moves between agencies, how models respond to irregularities, and how well predictions hold under real measurements. It wasn't an emergency drill, but a readiness assessment under realistic, safe conditions. As the campaign continued, combined measurements revealed patterns unseen in the first weeks. Positional data across longitudes showed subtle shifts in motion. The trajectory remained hyperbolic, consistent with an interstellar origin, but sunlight, dust release, and rotation interactions became clearer over time. Brightness data added another layer, showing that 3 Atlas did not brighten or fade in a perfectly smooth progression. As the weeks progressed, the global campaign on 3 Atlas began to reveal subtler phenomena that had gone unnoticed during the initial observations. Researchers started correlating brightness fluctuations with rotation periods inferred from positional changes, uncovering hints that the comet's surface might be irregularly shaped or possess regions with uneven activity. These brightness shifts, while small, were persistent, suggesting that certain areas of the nucleus released material more actively than others. Scientists recognize that this kind of heterogeneity is uncommon even in long-period solar system comets. And in an interstellar visitor, it offered a rare window into the physical conditions of an entirely alien environment. At the same time, the anti-tail continued to fascinate observers. Its persistence over several weeks indicated that the dust plane around 3 Atlas was remarkably coherent. Unlike most comets, where solar wind disperses fine particles rapidly, this interstellar object seemed to maintain a structured dust distribution, hinting at a unique combination of particle size, density, and initial ejection velocity. Detailed photometric studies allowed astronomers to model the dust's response to solar radiation pressure, revealing that some dust grains were deflected in ways that contradicted simple predictions. The degree of alignment and the subtle variations in tail orientation offered researchers a live demonstration of physical processes that are typically theorized but rarely observed with such clarity. Spectroscopic observations added another layer of complexity. Instruments capable of analyzing light at fine wavelengths detected hints of unusual compounds in the comet's coma. Preliminary data suggested the presence of molecular species uncommon in solar system comets, possibly volatile ices formed under conditions unique to another star system. Harvard and other academic teams began cross-referencing these readings with lab simulations of low-temperature chemistry, attempting to understand how these substances could survive interstellar travel and how they interacted with solar heating upon approach. Each new spectrum raised more questions than answers, underscoring just how little humanity knows about material from beyond our solar system. Meanwhile, the orbital modeling teams continued to wrestle with the non-gravitational effects. The hyperbolic path of 3 Atlas meant that even minor deviations could have outsized implications for predicted positions. Analysts experimented with dozens of trajectory simulations, accounting for jetting effects, rotational acceleration, and asymmetric outgassing. Some models suggested the comet was subtly accelerating along axes that didn't correspond to the main spin, implying complex interactions between surface structure, localized sublimation, and internal pressures. Each simulation refined predictions, but none produced a perfectly stable orbit. This imperfection, while frustrating in a predictive sense, was exactly the scenario agencies had hoped to observe, a real-world test of their ability to monitor, model, and respond to an object exhibiting unpredictable dynamics. The international collaboration also highlighted a striking contrast between professional and amateur observations. As the comet approached its perihelion, the pressure to gather detailed observations increased. Though 3 Atlas posed no threat, every day represented a diminishing window of opportunity. After it passed the sun, the object would accelerate away and fade into the depths of interstellar space. Teams coordinated shifts, sharing data across continents in near real time. Automated software pipelines ingested images and photometric data, producing refined brightness curves and motion plots within hours. Researchers debated subtle anomalies in nuclear shape, dust ejection patterns, and spectral lines,